Hello students, today we are going to study next demultiplexer 1 to 4 demultiplexer 1 to 4 demultiplexer. For 1 to 4 demultiplexer there are the 1 to 4. 1 to 4 means 1 input D in, 1 enable line, 4 output lines Y0, Y1, Y2, Y3. These are the outputs line, 1 input line 1 to 1, 1 to 4 demux, 4 output line. And how many number of select lines required? There are the 2 select lines are required, 2 raised to 2, that relation in n is equal to 2 raised to m, where n is equal to number of output line, where m is equal to number of select line. When there are the 2 select line, then output is n is equal to 4, that n is equal to 4, so number of select lines are required for 4 demultiplexer are 2, that S1 and S0, S0 and S1. This is the block diagram of 1 to 4 demultiplexer. Next, truth table. N E enable, D in input, S1, S0 and outputs are 4, that Y0, Y1, Y2, Y3. These are the outputs and these are the outputs Y0, Y1, Y2 and Y3. Next, whenever enable is 1, for D in data is 0, for D in data is 0, then S0 and S1 are 0, 0, S1 and S0 are 0, 0. So output Y0 is selected. For Y0, D in data is distributed, so Y0 output is 0. Y0 is output 0 and this is the 0, 0. When enable is 1, enable is 1 but D in data is 1, but select lines are 0, 0, output Y0 is selected, because select lines are 0, 0, but for D in data is 1, output Y0 as a 1, because the D in data as a distribute for Y0, because S1 and S0 are 0, 0, Y0 output is selected. These are the 0. Next, when enable is 1, D in data is 0, but S1 and S0 are 0, 1, 0, 1 means output as a selected as a Y1 output selected. For Y1 output, D in data is routed, distributes, that D in data is 0, so Y1 is here 0. Y1 is 0. This is for dark, that Y0 select, Y1 is selected. Next, when D in data is 1, then enable is 1, for D in data is 1, but select line 0, 1. Select line 0, 1 means output Y1 is selected. For Y1, D in data is routed or distributed. For D in data is 1, so Y1 is 1 and other are the 0. This is the Y0. This Y0 is connected D in. Y0 is connected D in. Here Y1 is connected D in. When enable is 1, for select data, for D in data is 0, but select line data is 10. 10 means 2 in a 2-bit. So Y2 output is selected. That D in data is routed to Y2. So output here is a Y0 and other are. When D in data is 1, enable is 1, for D in data is 1, select line input are 10, means Y2 is selected output. So for Y2, D in data is distributed. So for Y2, that output is 1, otherwise it is 0. This is Y2 is connected D. When enable is 1, for D in data is 0, but select line select the data as 1, 1. So Y3 output is selected 1, 1. In 2-bit, that 1, 1 is represent 3. So Y3 is selected. For Y3, D in data is distribute. For D in data is 0. So Y3 here is here. And for this Y3 we have to dark circle here. Next, when enable is 1, D in data is 1. For select line data is 1, 1. For select line data is 1, 1. So Y3 output is selecting. For Y3, D in data is 1. That D in is distributes for Y3. So here Y3 is 1 and other are 0. This Y3 is connected to D in, connected to D in. This is the demultiplexer 1:4 demultiplexer. And from this demultiplexer, you have to design the equations, and from this equation you have to realize the diagram. From this equation, where is y1, y0 is 1 here. For the output, where is y1, y2, y0, y1, y2, y3 are 1, that input line is considered, and you have to directly form truth table without K-map simplification. You have to write the equations. So y0, this is y0 is here 1. For that y0, you have to take the inputs as a here E, this is the D in 1, S1 and S0 are 0, 0. So S1 bar, S0 bar. This is the y0. Here is y1 is 1. Here is y1 is 1. For y1 output, input is selected as this line. Output is here y1 1. That input line is you have to consider for equation. Y1 is this E is 1, E1. This is the D in. Next S0 and S1. S0 S1 bar and S0 is 1. So this is a S0, not bar. Next y2. Y2 is here 1. Y2 is here 1. For that, these are the inputs and these are the outputs. Input for output, where is 1, that input line you have to consider. That E, this is E, this is a D in, and 1 0. 1 0 means 1 0. S1 is 1, so S1 and S0 bar, that is a 0. Next y3 is here 1, that input line you have to consider. Y3 here is 1, that input line you have to consider for equation. This is the E, D in, this is S1 and S0 are 1 1, so this is S1 and S0, not bar. And from that truth table, where output is 1, that input line you have to consider, and you have to write the directly equation without simplification K-map. After that, you have to realize the diagram. E, D in, S1. For S1 you have to connect the NOT gate, and for S0 you have to connect one NOT gate for S0 bar. This is the S1 bar, this is the S0 bar output. Next D in and next D in. E, this is Y0. There are the separately equation, not in a demultiplexer you have to add that all, and so here one OR gate is, but in here let's say there are the one input many outputs are different, so 4 AND gates are required. This equation is E. For E we connect here. Next D in, next S1 bar, S0 bar, so output this is a Y0. This form this equation. Next AND gate is required for Y1. Y1 equation is E, next D in, S1 bar, so here S1 bar and S0 bar. This is a Y1 equation. Next equation Y2, E, D in, S1, sorry, in this equation S1 bar, S0 and S0 bar. Here we connect S0. So this is the Y2. Next Y3. Y3 equation as a E, D in, S1 and S0. Here we for S0 we connect. So this is a Y3. This is the diagram for 1:4 demultiplexer. And in this one question is asked, implement that equation as a using NAND gate. In this question is asked 1:4 demux design NAND gate. So in this NAND gate equations we first convert in a NAND gate. That equations Y1 this E, D N, S1, 0 we convert in the into NAND gate. This is our equation Y0. Y0 equation is as E, D N, S1, S0. We convert this equation in a NAND gate. So that equation E, D in, S1 bar, S0. We want that diagram is only in a NAND gate. So in complete diagram, that NOT gate or AND gate or any gates are only in the form of NAND gate. So this equation we convert in a NAND gate. So take the double inversion, S1 S0 bar E D in double bar. This is the double bar. Original term is double bar is represent original term. So here is this equation is in the form of NAND gate. That NAND gate equation A into B complete bar, that we convert this equation into the NAND form. Next Y1 equation E D in S1 S0. So this equation is into NAND form, E D in S1 S0 bar. We not use here De Morgan's. We want the equation in the form of NAND gate. So take the double inversion of that equation. Next Y2 E D in S1 S0 bar. For this equation we take the double inversion, S1 S0 bar double inversion. This is the equation. Next Y3 E D in S1 S0. This is the equation for Y3. This equation convert in the NAND form. So take the double inversion for that equation, S1 E D1 S1 S0 double inversion. And for these all equation Y0, Y1, Y2, Y3, these are in the form of NAND gate. So this 1:4 demux using NAND gate. For you have to design that only in a NAND gate. So this is equation E D in for S1 and S0 bar. So that diagram only we realize using only NAND gate. So this is S1 and output of that NAND gate is a S1 bar. That NAND acts as here inverter, acts as a inverter, not because we design that demux as a using only NAND gate. So this here not we take the NOT gate, but diagram, in a diagram we want only NAND gates. So here and NAND gate acts as a inverter. Next for S0 we connect NAND gate and output of that S0 bar. Next this diagram is only in a NAND gate. So NAND gate, that is S1, next S0 bar D in E. This is the for first bar, for this the first bar, and we connect another one NAND gate for this upper inversion. So for this NAND gate, that equation is E D in S1 bar S0 bar, one single bar, but output of that is NAND gate is final E D in S1 bar S0 bar complete bar, double bar for this Y0. Next E D in next S1 bar and S0 and another one bar for that equation. So we connect here one. This is the Y1 equation, this is the Y0. Next one AND gate for Y2 we connect one NAND gate, that equation E D in S1 S0 bar and this is the equation for one single bar, for this single bar, and for another bar we connect one NAND gate. So this is the output of Y2. This is the output. This complete equation is here Y2. Next Y3. For Y3 the diagram is only in diagram is a NAND gate, because we designed the 1:4 demux using only NAND gate, So in this SE, next is D in, next S1 and S0. So here S1 is connected, S0 is connected. This is in this, for this NAND gate there is equation for single bar, and for another one double, here is a double bar. For another bar we connect one NAND gate, So this is the y3. This is the y3. That diagram we design using only 1:4 demux, using only NAND gates. This is the designing. Next, 1:4 demultiplexer. 1:8 demux. 1:8 demux. Only I am giving here block diagram. You have to design the truth table for 1:8 or 1:16 demux. One data input line, one enable, 8 outputs y0, y1 up to y7. These are the outputs, and 1:8, 2 raised to 3 is equal to 8. So select lines are required, S0, S1 and S2. 3 select lines are required. 1:8 demux. This is the block diagram of 1:8 demux. And from that you have to design the truth table as a enable is 0, enable, then S2, S1, S0, and outputs from y7, y6, y5, y4, y3, y2, y1 and y0. These are the outputs of 1:8 demux. These are inputs and these are the outputs. And enable is 0. Demultiplexer not start its work. So enable is 0. S2 0. S2, S1 are don't care. So all outputs are in a 0, 0, 0, 0, 0, 0, 0. When enable is 1, S2, S1 are 0, 0, 1. So output D in, this input is routed to Y0. So output here is a D in, and other are the 0, 0, 0. When enable is 1, S2, S1 are 0, 1, 0. 0, 1, 0. So output Y1 is selecting, because input for select line 0, 1, sorry here 0, 0, 0. So 0, 0, 0, D in data is routed to Y1. 0, 0, 1, 0, 0, 1, 0, 0, 1 means Y1 is output selecting. So for Y1 is data, D in is routed. Next, enable is 1, 0, 1, 0. This is a 2, S1, S2 are white. This 0, 1, 0 means number 2. So output Y2 is selecting. Output Y2 is selecting. For Y2, distribute the data D in as a Y2. Next, when enable is 1, 0, 1, 1 means Y3 output is selected. For Y3 output as a D in is routed or distributes. So here is a D in, otherwise 0. 1, 1, 0, 0 means 4. Means output Y4 is selecting. Output Y4 is selecting. So output for Y4, there is a D in data. This is for Y4 is distributed. So D in data is for Y4. So this is a 0, 0. Next, when enable is 1, 1, 0, 1. 1, 0, 1 means 5. So output 5 is selecting, and for Y5 there is a D in data is distributed. So here is a D in 0, 0, 0. Next, when enable is 1, 1, 1, 0. 1, 1, 0 means data 6. There is a 6. So Y6 output selecting. For Y6, D in data is distributed. So for Y6 there is a D in, and other are 0. Next, when D in is 1, enable is 1, there are the 1, 1, 1 select line. The data is 1, 1, 1. Data is 1, 1, 1. So Y7 output is selecting, and for Y7 D in data is distributed. So here is a D in, other are the 0, 0, 0, 0. This is the 1:8 demultiplexer designing, and it's a truth table. And for 1:16 demultiplexer, there are the required 1:16, one data input, one enable, and from Y0 to up to Y15 outputs, 1:16 demux, and S0, S1, S2, S3, 4 select lines are required. 2 raised to 4 is equal to 16. So number of select lines are required for 1:16 as a 4. 1:4. This is the 1:16 demultiplexer. For this you have to design the truth table. This is your 1:4, 1:16, 1:4, 1:8 or 1:2 demultiplexer we have designed. In 1:4 one question is asked that implement using NAND gate. That problem also we take. Next is a that demultiplexer tree and comparison of demultiplexer. In the next lecture we study, and for this multiplexer we require the different ICs, that is a 74155, 7415, that is a 1:4 or 2:4 decoder. That demux is acts as a decoder. Why this demux is acts as a decoder, we study the next lecture. In the next lecture, tree and comparison we study.